So this video is going to be a continuation from our binary search tree, and so we're going to be implementing an AVL tree, and I'm hoping to keep this one very short because once you understand how a binary search tree operates, I think implementing an AVL tree is quite trivial. Okay, so AVL, I can't remember what it stands for, but I do know that it's supposed to represent the initials of the people that came up with this pretty clever idea, to be honest with you. And so why do we even need this, right? So suppose we have this example here on the right hand side of some skewed binary search tree, right? So we have 1, 2 all the way up to some number n, and suppose then that we wanted to, for instance, search for this nth value here. We would have to go level by level by level, right, in order to find it, and for a total of n levels, and so that's O of n. It's linear time. It's really not efficient at all. It's because this tree is what you call unbalanced, right? And so an AVL tree is just a modified binary search tree with some special constraints on it. And so I'll be going over those constraints with you in a few. And so I'll have to go over, first of all, the small changes that I've made in the code so far. Okay, so let's start with the struct itself. We've added a new attribute here called height, right? And fair enough, every single node, when it's initialized, the height is already set to 0, okay? And inside of the insert function, we have something called update height, right? And then, so the insert function is much the same, right, as the last time around. So let me find the insert function for you. Here it is, right? It's much the same. The only thing that's new is that we have some update height function, which I'll go over with you in a second. Then we have something else here called the check balance, right? I'll go this over with you as well. You have to calculate something called the balance factor. So that's the second function, right? And then if the balance factor is not within range, and so the range for the balance factor is -1, 0, and 1. If the balance factor doesn't fall within this range for any given node, it means that that node, right, is unbalanced then. And so you would have to perform a rotation in order to balance the tree, all right? Okay, so I think this is best served though by an example, right? So I'll run through an example and we'll go through the functions and we'll walk through this bit by bit. It really isn't as complicated as I think people make it out to be, but of course, maybe I myself do a terrible job of explaining this. But okay, I'll try my best anyways. And so we'll start with, I don't know, let's start with 10. We always start with this number 10. Right, so let's suppose we inserted the value 10 into our binary search tree. What's going to happen is that it's going to run the insert function as per normal. The null case is going to trigger and it's going to break out straight away, right? This should be fairly standard to you by now, especially if you understand how the binary search tree is operating. Okay, and then obviously the height is going to be set to 0, right? Remember, every single time you create a node, the height is going to be set to 0. But nothing here is going to run, right? Because remember, it's breaking out straight away at the null case. All right, then. Suppose then we inserted the value 11, right? What's going to happen then is it's going to come in here, find the null case, throw it back to the caller, right? This should be already familiar to you. And then 10.11 is going to be set, right? 10.write, which is 11, so that's going to be set. And then it's going to continue on, and it's going to update the height now. So what is this update height function? Well, it's quite simple, really. I'll show you the implementation, and you should be able to see that it's not at all anything to be stressed about. Okay, so if you don't find a node, just break out, right? There's nothing there. And so you find the height of, you get the height of the left child and you get the height of the right child. And so this height function is just going to return the height of the node that you put in here, right? Whatever pointer you put in there, it's going to return back the height. And if it's null, right, it's going to return -1, which is an important bit of information to know as well. Okay? And then what it's going to do is, this is just a ternary operator. You don't have to use this if you don't want to, but it's going to compare the two, right? And it's going to return whichever one is greater, pretty much, right? So it's going to return the larger of the two heights, and it's going to add 1. Okay, so that's pretty simple. So it's going to, right, find the height of the left child, which is -1 because there's nothing here, right? And then it's going to come and check for the height of the right child, which is 0, right? This one's set to 0. And it's going to say, okay, well, which one is greater? Well, obviously 0 is greater than -1, so it's going to return 0 plus 1, okay? So it's going to update that height. And so the height here is going to change from 0 to 1. Okay, and this guy's height is 0. So do you see that the height is growing quite literally? So we know that the height is 1 now. Okay. and then it's going to check the balance for the root node, right? And so how it does that is, let me get this. So what it does is it'll go height of left subtree minus height of right subtree. I had to abbreviate that. So it's going to take the height of the left subtree, right? And it's going to subtract that from the height of the right subtree. And that's going to be your balance factor. And if the balance factor doesn't fall within this range here, -1, 0, or 1, for any given node, right? And currently we're calculating the balance factor for this guy, right? Because that's where we are after we returned out from this function call. Then it's going to have to perform a rotation. But let's see what we're dealing with here. And so it's going to say height of the left child, right, or the left subtree, it's -1, minus the height of the right subtree, which is 0, and it's going to give us -1. Okay, and so we do see that -1 does indeed fall within the specifications, and so we don't have to do anything there. Now suppose then that we inserted the value 12, right? Inserted the value 12 here. What's going to happen? Well, it's going to throw out back straight away from the null case into 11's function call. 11.right is going to be set, right? Then it's going to come down now and update the height for this node now. It's going to update the height, and we know that the height is simply just comparing the two. So this guy's height is 0, 0 plus 1, right? And then it's going to check the balance, and we already just calculated the balance for this case. It's quite literally the same here. So the balance is going to be -1, so that's fine. Going to continue running, and then it's going to throw up back to the caller, right? So now we're in this function called 10, right? And it's going to do quite literally the same thing. It's going to grab the larger of the two heights. Now this is 1, right? And so 1 plus 1 is 2. So the height is going to be updated to 2. Okay, do you see now, like 0, 1, 2, how this update height function is working, right? And then it's going to calculate the balance. And so the balance now is going to be the height of the left subtree, which is -1, right, minus the height of the right subtree, which is 1, which is going to give us a value of -2. And we see that this falls outside of the scope of what we're allowed to do, right, in the AVL tree. And so we're going to have to perform what's called a rotation, right? And so now there are 4 cases for rotation. I'm just going to be showing you, I think, 2 of the most important ones, and then, well, they're all important, quite frankly. But I think there's one case you need to see, and you can literally generalize it, or at least I've been able to generalize it to all 4 of the other cases. And I think this isn't too difficult either, but I'll go ahead and show you. We'll start with this example here, right? And so this is what you call a right of right insertion, right? Because this is the node here that's becoming unbalanced, right? And the insertion was made to the right of right. Do you see that? So this is referred to as a right of right case, okay? And let me try and find, where is that? Here it is, right? So if the balance factor is less than -1, right, we know that the tree is heavy on the right hand side, and this is the case that we've been dealing with so far, right? The balance factor is -2, okay? But there's 2 cases. There's right of right and there's right of left, okay? That's where the node we inserted could have been, right? So had we inserted the value, for instance, 10.5, right? If we'd inserted 10.5, it would have been over here, right? It would have been a right of left insertion. But that's a different case, okay? I want to cover this general case first, the right of right case. Okay, so, and what you do is, it's quite simple, to be honest. You do what's called a left rotation around this root node here. You literally drag everything up. But I think the best way, though, is just to show you by example. And so I think, yeah, I think so. That's probably the best thing to do. We'll go over, like, visually how this is functioning, and then we'll take it from there. So let me draw everything back. Let me go, oops, 10. Oh, that's not 10. So this is 10. This is 11. And this is 12. Okay, and so when this rotation is finished, right, I don't know if you can imagine this in your head, right, but instead of this guy here being the root node, this middle node here, 11, is going to become our new root node. So this is going to be our root node, right? 10 is going to have to be to the left of it, right? 12 is going to be to the right of it. So I don't know if you can, like, see this inside your head going on. So we're going to have to change the structure to make this the new root node, right? And so 10 is going to be to the left, 12 is going to be to the right, but there's also something else that's important. Originally, right, 11 had something popping off to the side, right? We can call this X, for instance. Or let's do it like this. Let's say A, B, this is node A, node B, and node C, right? And then we'll say this is B's left child, like so, okay? Right. And so you can imagine then that once this is finished, right? Once this rotation is finished, let me see if I can select this. Can I rotate it? So it's gonna look something like this, right? Okay, I can't move this, but if you can imagine, this was like a little bit higher up, and then we would move this left subtree here. Okay, this is really terrible. This is just very, very terrible drawings. I think this is best done with an animation, so I've just tried my best to get this point across though. However, the point I'm trying to make, and I'll just articulate it, is that the left subtree, right, is going to go to the right of this node here. Okay, so BL is going to go there. And then this would have its 2 children node like so, and this already has its 2 child node, and then this is allowed to have 2 child nodes as well. Okay, so hopefully that wasn't too badly explained, but I think I'm going to need to go that over again, just in a bit more organized fashion. So we've got 10, 11, and 12, right? And so this is actually what I was trying to do. So 11 becomes the new root node, right? And then 10 obviously was going to go to the left of it, 12 is going to go to the right of it, right? And then remember, then originally there was some subtree sticking out from here, right? And that is going to go, suppose this was 10.5, right? Suppose this was 10.5 here. Let's just say, as a contrived example, there might be nothing here, right? But suppose there was something there. Then it would have to come to the right of this guy here, okay? Of A. So 10.5. This is what the point I was trying to get across. And if you can burn this configuration into your mind, I don't think you're going to have any problems at all, to be honest, understanding how these rotations happen. And so let's actually go into the code and see what the left rotation is doing. And so here it is, left rotation of some node, right? And so you can see B is equal to node.right, okay? So this is, as I was explaining, this is A, B, and C, right? A in this case being the root node that we put in as the parameter, right? So root.right is going to be equal to B, right? So now we've got B, and then BL, right, is going to be B.left. So that's quite simple. Oh no, the music's here. But okay, so this is going to be B.left, right? Good, so we've managed to establish that. Now if we're making this guy B the new root node, right, then obviously we need to set its parent as well, right? Okay, so B.parent is going to be equal to node.parent, and then node.parent is going to be equal to B, right? Because BA, right, or the original node that we put in, its parent is going to become B, right? Let me put this in. So this is A, this is B, and this is C. Okay? And then B's parent is going to be whatever A's parent was originally, right? So maybe in the first contrived example, then A originally had no parent, right? Because it's the root of the binary search tree. And so now B's new parent would be null in this case, right? Once this bit of operation here was carried out. Okay, so node.parent is going to be equal to B, and then now we check for the left subtree if it does exist, right? If the left subtree does exist in this case, if something is here, then we need to set its parent to be A, right? Because remember we said we're putting it to the right of A. Remember that. So we check that box there, and then B.left, right, is going to be equal to the node. So we put A to the left of B, right? And then node.right, okay, so node is A, and node.right is going to be equal to BL, okay? And then we don't have to do anything with C. C is already in place here. So that's how this rotation happened. Alright, hopefully that's clear to you. And then you just return B, okay? And it's pretty important that you return B, by the way, because I hope you understand by now that the binary search tree is actually just recursively building itself as it returns to each function call, right? And I already spent so much time going this over in the binary search tree example, but I hope by now it's clear to you why this return might be important here. And so that's a left rotation. Okay? And so I'm going to show you the right rotation now, which is quite literally just the mirror of the left. So the right rotation would look like this. Okay, so we just did the case for this one, the right rotation. This would be A, this would be B, and this would be C. And the configuration you're trying to get, right, is B up here, A down here, C here, and then remember now that B might have some subtree. I didn't draw this properly. Right. So B might have some subtree here, right? Hopefully that's clear to you. So I think this is always best served just with numerical examples. So let's just go 10, 9, 8, right? And then suppose we had 9.5 or something here, right? Then what would happen is that 9 would become the new root node, okay? 10 is going to go to the right of it, so we're maintaining the property of the binary search tree. 8 would go here, right? And then now we have to decide then, okay, where we're going to put this 9.5, and it's going to come to the left of this guy here. Okay, so it's going to come to the left of 10, so it's going to go 9.5. It's going to come here. So if we come up here to rotate right, then node new root dot right is going to be equal to node. Yeah, so node dot left is going to be equal to the moved subtree. So yeah, that's just about right. So in this particular setup that I have here, so this is the root. This was the original root node, right? And this guy dot left is going to be equal to the moved subtree. So yeah, this is the configuration for the right of left, right? So we've done left of left, we've done right of right. Now I need to show you right of left, okay? And then you can generalize to the other case as well. So third page after, oh, before. Okay, and so we've seen this case, right? And we've seen this case over here as well. So we know what the right and the left rotations look like. And so there's two more cases as well. There's this one here. Okay, so right of left, right? And then there's this one here as well. Left of right. Okay, so these are the four configurations you need to know. However, if you only know one of these configurations, like this one here, for instance, then you can generalize it to all of the other cases, because you see, right, that this left of left is just a mirror of right of right. Okay, so if you can implement one of these, you can implement all of them. But so this is why I'm going to show you. I'm going to show you this one here, right of left, and then I'll leave you to figure out how to do this one, because it's just the same thing again. All right, so what are you doing here? Let's say we had 10 and 9, whoops, gotta be 11, and then maybe 9, right? Well, no, it can't be 9, it has to be, so I'm gonna say 12, and then I'm gonna say 11, like this. Okay, so suppose this is what we were dealing with. So you come down here, if you take a look at the insert function, right? In the other case, okay, so this is the right of right case, right? And you can go ahead and examine this statement if you'd like. I don't want to spend too much time on that. I've already gone over what string compare does in the last bit. So, however, this is the other case now, right? Right of left case. And so what you do is you perform the rotation, right? And you do a right rotation on the right node. Okay, root dot right, you do a right rotation on it. So this is the root that we're doing the rotation on initially, right? And then inside of here now, we're gonna set that root dot right value to be equal to another rotation on this guy here. Okay, so we're going to perform the rotation on root dot right, which is this guy here now, okay? And we're setting that value at the same time. Hopefully that's clear to you what's going on. And so what does this rotation look like on this piece here? So, and the rotation we're doing is a right rotation, right? And so and we've already been over the right rotation as well. So this is going to be 12, this is going to be 11, and this is null here, right? And so hopefully it's already clear to you what you need to do, right? So this is A, this is B, this is C, right? And this is X, or B of L, or whatever you want to call it, or B of R in this case, but we'll just say X or whatever, right? The subtree that you need to move, essentially. And so what you do, right, is you quite literally just make B, it's the same thing, right? So 11 is going to become the new root node for this particular subtree, right? 12 is going to go to the right like so. Null is going to point off like this, right? And then X is going to go to the left like so. Okay? So this could have been 11.5 here, for instance. 11.5. If there was 11.5 in place of X, then it would have come here, okay? 11.5. Oops. Okay. Alright, my drawing is very, very bad, but I hope I'm just getting the point across. Okay? And so, now, what we have, right? And so this quite literally doesn't matter though, so I hope you get the point though. It's this X, right? So it's pretty important, and the algorithm should be clear to you as well, what's going on there. And so now, this guy becomes the new root, right? And so it's returned back to the caller here, right? It's returned here, and then root.right is being set, okay? And so root.right is now going to be whatever that returned back. So this is going to be 11 now. Do you see what's going on here? And so the root is starting off as being 12, but now that we set the root.right, okay, it's now being 11. So root is 10, root.right is 11. Okay, 11 was pointing off to null here. This is what we have down here. And then this is pointing to 12 like so. Okay? And do you recognize this configuration? We've managed to successfully reduce this problem down into something we can solve. Do you see this? This is the right of right case, right? And if you look down here, then you just do the left rotation on this, okay? And you're done. So it's broken down into two rotations then in that particular case. So the first thing you do is you reduce the problem down into the right of right case, and then you perform the left rotation on this now. Okay, so you perform left rotation on this root node, and you're good to go from there. The tree will balance itself. And the same thing happens for the other case as well, right? So we covered this case here, and the same thing is going to happen here as well, okay? But just in a different fashion, okay? So in this particular case, it's going to do it on the root.left, right? And it's going to do a left rotation, and then it's going to do a right rotation. So quite literally the mirror opposite of what we just did here. Alright, so I hope I didn't do too horrible of an explanation, going over an otherwise, I think, simple topic, but yeah, that's my short video on AVL trees, and the deletion is very much going to be the same principle as well. I'm not going to spend any time going over deletion with you. I'm going to leave that for you to figure out, but I think you've got enough in the tank now to be able to figure out how deletion should work as well. Okay, so hopefully you guys found this at least somewhat helpful, and I think this video would be best suited if you had watched something else related to AVL trees, right? I think more so what's important though is to just get a couple of concepts across, and yeah, you figure it out from there. Right? How to implement the code is really not as important as understanding what's going on. Alright then, well, thanks for watching, and if there's something you think I might have missed or something you don't quite understand, feel free to ask in the chat, and I'll be happy to reply to that.